Morning, everyone. Thank you for being here. We're not in the program. We are presenting backup presenters. So thank you very much to Michael for allowing us to present now today. We're going to present the ArgoMoon satellite. For who are not familiar with this satellite, will be part of the exploration mission 1 from NASA in the S.r.l program, and we will basically be in it's the same mission of lunar flashlight that has been described yesterday on the top. So just one slide really brief about the company. We're a company based in Turin with a couple of other offices in Europe. We do a lot of things related with space, spanning from design of different kind of systems and till operations. And we are quite a young company. It's 10 years established, and we tend to work a lot. Also thanks to the really low average age, we work a lot with also university in terms of collaboration. We are not really looking for selling things, but really to collaborate with ideas of universities around. And it's really interesting to see all the concepts described in these 2 days, because basically in this presentation we will give an idea on how we practically deal with the design and production of a CubeSat for deep space exploration. So that's our mission, the concept, a description of what will be our mission. So basically, we will be on board the maiden flight of S.r.l. next year. Basically, it's the planned launch date at the end of the year. We will be together with other 13 CubeSats, mostly from NASA. But we are also there. And we have basically 2 phases of the mission. The first one is to take historically significant pictures of the stage from which we are released from, which is the ICPS stage of the S.r.l. launcher. This is a really short first phase of the mission, and we will document the status of that stage in orbit to detect possible damages, and then we also document the release of the other satellites, the other CubeSats, which one of them is, as I say, lunar flashlight. Then after this, we will enter to a geocentric orbit, really elliptic. It will bring us outside the protection of the magnetic field of the Earth. So in our design, we consider basically deep space conditions. And the planned lifetime is 6 months for the mission, but we are evaluating some extension. So here's some facts about the satellites. Just let me point out, it's a 6 units plus CubeSat, and it's 14 kilograms. And these are requirements strictly derived from the NASA constraints from the launcher. Power 80 watts provided by solar panels, as Ismael described, from DHV Spain, and also backup as a battery. And then we also a propulsion system for both orbit maneuvers and altitude maneuvers, with green propellant and cold gases for as a secondary propulsion. The payload, as I said before, we will take pictures. So there's a a double optical system with a broad field of view and a narrow field of view, the telescopic view, and then a rangefinder also to allow us to. One of the things that we will do is tracking of the ICPS. So we'll use also rangefinder for distance measurement. There's again just an image of how we managed to put all these things inside the satellite. And then just a short description about the subsystems. So these are the two developed in-house. For the power control, so the power control boards, electronics, and the onboard computer and data handling subsystem. The main driver, of course, was to stick radiation-hardened design into a really in a CubeSat constrained dimensional space, and we come up with this solution that takes up one unit. Continuing with other subsystems, so as I said, the payload, you can read some facts. Of course, some of the information are restrained, so constrained, so we cannot provide that. But I guess that some of the subsystems you are probably familiar with, in the propulsion system especially. So it's a mixed supply chain from European and US-based suppliers. And as I said, the battery, which is a backup for the solar panel while not exposed to direct sunlight. And then the other systems, there's another one that maybe you are probably familiar with, the radio system. And then, as I said, the rangefinder and the altitude and determination control subsystems. The driver, of course, was to select components with radiation assurance or flight heritage. One other thing, really important thing that also we developed in-house is the image recognition system software. So which is one of the things that our onboard computer and the handling system can do. The image recognition is really important. It provides basically the information important also for navigation and tracking, and it was built with a modular approach. So we start off with really important things, which is the image system subsystem 1, which is just for the first rough identification of the target. Then, as soon as we go forward, we can optimize that so it kicks in another layer of the software that is for the identification of the center of mass. In addition, the possibility to, with this process, the possibility to identify multiple targets. So we will see, because we will be in view of in some condition, Earth, Moon, and ICPS, which is really close. So we need to consider multiple targets, and then at the end, the really optimized approach, which is the fine recognition of these multiple targets recognized with the layer, the previous layer of the software, and then other usual things that are dealt with, like housekeeping and these normally activities for our onboard computer. So as I said, we try to be really, really brief. So the take-home message for us is that for our experience, to deal in practice with the implementation of a CubeSat for deep space, it's really important to maintain a balance between these three main factors, namely costs, and I would say also schedule, performance, and reliability. Because it's a trade-off. We realized pretty soon that it was a trade-off between these three aspects, and well, this was our how we did it. We are currently reviewing the results of the tests, so ground model TRB, and also we already started the production of the proto flight units. And also in that case, another change of paradigm, something that I heard yesterday, it's also to reconsider the allocation of the tests and for between the engineering or qualification model and the flight model. So that's another way to obtain a qualified system with an alternative approach, so fully qualified, but in saving costs, saving money and time. And then that's our proposal, like maintain high performances, reliable design, the radiation hardness, which is a really important thing, not only the total dose, but the single events. That are probably I mean, in our case, for 6 months mission, not really the total dose, but the single events are really something to be taken into account. And then tricky navigation algorithm that we developed in-house, and to stick everything in 14 kilograms unit. Really important also is to be compliant with the normative and standards. Our customers for this satellite is the Italian Space Agency, so we stick to the ACSS standards. But also we have NASA requirements, so we need to also take into account all requirements, for example, for safety or launcher integration. And that was quite a challenge, but actually we are handling that. So another thing is that, of course, there are, once it comes to engineering, it's something to be taken into account is the standards and the workmanship standards, these kind of things. Another thing that we're quite proud of is the quite reduced time from concept and flight delivery, planning delivery, reducing respect with, of course, larger satellites. And of course, we are considering to use the experience that we gained with this specific project, really challenging project, also to validate the platform to be used for future mission. And that was really all from our side. Thank you. Just one thing, you may have noticed that we missed one of the most crucial subsystem, the solar panels array. But of course, it has been really good described by Ismail. So, yes, but of course, solar panels are also important subsystems also. Thank you.
Okay. Are there any quick questions? Otherwise, I might try to break this.
What are you doing for single event test, obviously?
For single events, of course, we have selected from the beginning radiation hardened components that can also handle with single events. And then we have latch-up system protection. So we have dedicated circuits to protect the really few commercial components that we use. So that's the approach. Additionally, bolt design, because a bolt approach, because we have to double the layer of the main structure outside of the satellite, and we have another inner protection of aluminum that protects the power and data input unit. So both the onboard computer and the electric power system are also in a dedicated box, aluminum box. So it's a double protection. Additionally, we have basically 5 boards. We also designed a system to put the commercial components that anyway needs to be upstreamed. That was a process also in accordance with our customers. So anyway, we need to characterize the commercial components, and once we put them in the design, we put them in the middle of those layers. So outside we have the radiation hardened components, and really inside protected the commercial components. And as I said, that has already been also characterized. So if we use commercial components, we need anyway to use something that has already flown, at least, or additionally perform some additional upscreening.
Do you have a budget?
Yeah, we have it. Of course, it's restricted information, but our customer is the Italian Space Agency. We have no budget allocated for this project.
Okay, can I suggest any other questions?
Yeah, of course.
Sorry for running a bit behind, but let's thank you all. Speak again.